First of all, I'd like to thank the organizers for this kind of invitation to talk here. And yes, as the title says, as you just heard, I would like to talk a bit about possible way towards a better understanding of cosmic acceleration and how this could potentially be a question of life, the universe, and everything. And yeah, just let me make a slow start here. I'm sure everyone is familiar here with this cosmic pie chart, which depicts the energy budget of our universe today. And as we know, we have it's roughly composed of 70% of a substance that called dark energy that is the responsible component for the observed late-time accelerated expansion. And of course, the best candidate we have for that is a cosmological constant. But with that come a range of problems, which can be divided into some old aspects, but also new aspects, of course. The old aspect is that, of course, people already were aware of some issues here with these equations when even before in the late 90s, we've had finally evidence for cosmic acceleration, late times, is that, of course, in empty space, you would expect not a zero energy contribution, but the vacuum fluctuations that add here come into play here. And when you calculate this, then you end up with a number that would be way too large to even allow for structure to form. And so the conjecture was that perhaps there would be some symmetry or some mechanism that would prevent vacuum energy from gravitating. But then, of course, in the late 90s, we had then the evidence that there is late-time acceleration, which can be explained with the cosmological constant. But of course, the value that we need for that is much smaller than our naive quantum expectations that we can compute. And it's 120 orders of magnitude off. And on top of that issue, we have, as you can see here, a coincidence problem or a why now problem, the question of why the energy density in the cosmological constant happens to be of roughly the same size as the rest of matter today. This wasn't true in the past and won't be true in the future, as we know, because of course they evolve differently. And there's some ideas that perhaps understanding this coincidence may lead to a deeper understanding of the dark sector. And of course, something that's been very popular over the past years has been to perhaps implicitly at least adopt still that there should be some mechanism that prevents vacuum energy from gravitating, but then attribute cosmic acceleration to something else, like a dark energy field permeating space, or perhaps even a modification of gravity on very large scales. And I should say that these models predominantly, they don't address the old cosmological constant of why vacuum energy does not gravitate. They just assume that there's something that hides that. But why modify gravity on large scales, for instance? And I think phenomenologically speaking, you can, of course, motivate that well. It's essentially, you can just imagine, for instance, being a being on the surface of an atomic nucleus, and having done some physical experiments there and determining that you understand the physics that dominates the world, and then you extrapolate your physics to the length scales that govern, well, the length scales of human beings. And of course, we know that there are not quite the same laws. And you could now say the same thing, at least the extrapolation that we do here in terms of length scales is very similar to taking the solar system, having performed our experiments here. We know that gravity behaves very much as Einstein predicted, that's general relativity theory. And then we extrapolate that to the length scales that crosses the entire universe. And so I think it's a very good thing to go and test gravity independently from our local tests with cosmology. And now maybe from the theory side, of course, if you want to find some theory of gravity that also is applicable at quantum scales, then you would come with well, extended theories that can give rise to effective fields that can enter, well, they can still be present in principle in the infrared. And you could wonder whether these fields could have any effects, for instance, on gravity on large scales. And so the simplest thing you can do with that is you introduce a scalar field. And the simplest, well, then of course you arrive at this action here. It's not, well, it's let's say the most general action you find with introducing the simple scalar field. And it comes with a lot of freedom, as you can see here. We have these four functions of the scalar field phi, plus its gradient derivative x. And you can then say, well, obviously with so many free functions, you ought to be able to describe some cosmic acceleration at late times. which doesn't use any dark energy or a cosmological constant. And so effectively you can do that. These modifications can be describing, phenomenologically speaking, you can realize cosmic acceleration in two ways here. Either you introduce an evolution in your gravitational coupling, or you introduce a deviation in the speed at which gravity propagates. Or it's really a combination of the two, and it's this dark blue shaded region at the edge of the plot. And of course, if you want to have an order unity effect in the background, you ought to introduce a significant magnitude in your modification, as you can see here. And if you have a strong modification, of course, you would expect that perhaps you can see this in other observables as well. So for instance, in the large scale structure. And you can individually test an evolving gravitational coupling very well with large scale structure. We can also test it, the modifications that give rise to a change in the speed of gravity that also affect the large scale structure. But there's so much freedom in this action that these modifications, they can conspire against you and produce the same large scale structure as standard cosmology. And then we get this dark degeneracy that extends all the way to the self-excited region. And I should say this is a region really where gravity is evolving such at late times that you don't need any dark energy to dump into the system or any cosmological constant to get this cosmic acceleration. And of course, this is a log-log plot, so there's significant parameter space that you have available here. But of course, what you can also see from this plot is that with measuring gravitational waves, we break this degeneracy. And in particular, with measuring the speed of gravitational waves to correspond to the speed of light, we are forced to this left-hand side of the plot, in which case we break the degeneracy. And if you want to explain cosmic acceleration with some genuine evolution of gravity, we have to occupy this upper left corner here, which we can then test with large-scale structure. But so this was just a forecast we produced in 2015 for what we should be able to do with a neutron star merger with electromagnetic counterpart. And so this was the measurement that we got with GW17 which matches pretty well here. And of course, the very strong constraint that we get here is coming from the gamma ray burst, which followed just something like 1.5 seconds or so after the gravitational wave event. And of course, for a signature or for a that has been traveling for roughly 100 million years or so through space, for two signals to arrive at the same time, or almost the same time. Of course, that means a very strong constraint on any deviation you could have between the speeds. But you can see we have counterparts here from gamma ray, X-ray, all the way to the radio. Some of these signals following only days later. So, but in principle, for our purpose, any single one of those measurements would have completely been sufficient if you could have made the clear association with the gravitational wave event. So even if they would have followed days later, we were looking here at an effect of order unity. So that means, of course, for a signal that's been traveling for 100 million years, we would have either seen the counterpart or none. I mean, not in our lifetimes at least. But of course, that we see the fact that we see so many puts us with confidence to this left-hand side of the plot. You have to occupy this region up here if you want to explain this genuine self-acceleration with gravity. And we can test this with large-scale structure. Now, this is also just a forecast of what we should be able to do with Euclid or LSST data, which we, of course, don't have yet. But since we were expecting, well, in 2016, we went out and looked for something that would already push beyond this minimal self-acceleration bound, since we're expecting something like GW17, and we found some useful data. That's galaxy ISW cross correlations in particular, and they already pushed 3 sigma below this minimal self-acceleration bound. I should say it's minimal. You can really, in the formulate here, theoretically, the minimal threshold you have to implement here in the Sondesky action so that they can fully attribute cosmic acceleration to evolving gravity. And now just to recap, the concept that we could explain cosmic acceleration at late times with the modification of gravity is, at least within this context of Sondesky theories, is at 3 sigma odds with the current data already. But of course, 3 sigma is nice. We want to push beyond that. We want to go to 5 sigma or more. Hopefully, we'll be able to do this with large-scale structure data in the near future. But also, of course, very interesting here are these gravitational wave distances or standard sirens, which have been proposed as tests to essentially measure the expansion rate of our universe, because from the cosmological propagation of gravitational wave, the cosmic expansion enters a Hubble friction into the gravitational wave equation, and so that the gravitational wave amplitude decays with the distance it's traveled. And so this has been used already to put an interesting constraint here on H0. Of course, it's not as competitive as other measurements, but it's completely different. And in the future, it will, especially with LISA or the Einstein telescope, we will obtain a lot of these data points here. Should say you don't necessarily always need electromagnetic counterparts. If you can really focus enough your source of the gravitational wave, you can maybe use galaxy maps to identify the source and associate the redshift. And so you have distance redshift relation that you can then compare against other observable data from other measurements. And so the fact is that if you would have a modification of gravity where the gravitational coupling would evolve in time, that would introduce another friction term. And you can compare this against the other luminosity distance redshift relations you get from other data, and then put a constraint on how much this gravitational coupling can evolve. Now, at least that was the idea. And somewhat more recently, we looked into this in more detail and found actually that for viable Horndeski theories, you shouldn't be expecting to see any signature here. And the reason for that is that if you want to have models that have large cosmological modifications, you want these models have to hide those in high density regions, such as the solar system, because by there we have already made very good tests that confirm general relativity. And yeah, so they come with screening mechanisms, and it turns out these screening mechanisms, of course, gravitational waves tend to originate from high density regions too. And so that would screen not only these modifications in our solar system, but also in the environment of the source. And so what you do test with standard science is just the net difference in this gravitational coupling, which for Horndeski theories in this case, you would not expect any signature in the end. Although I should mention that, of course, other theories work differently, and we can still find signatures for those. But even more recently, now we looked at this in more detail with actually the emission process, and performed a post-Newtonian expansion in the near zone and the radiation zone, where expected the radiation zone eventually becomes unscreened. And we find that there is some 1.5 PN order modification that potentially could be observable in the future. And so, yeah, the jury's not out on that. I think there's still a lot of interesting work to do in this direction. Maybe some more direct implications on this complicated action we've seen from this low redshift measurement from GW1707. That's really low redshift. It's at 40 megaparsecs, so we're talking about redshift of roughly 0.01. On these, there, of course, we have a strong constraint now in the action. Principle, of course, you could imagine that high redshifts, you would still have room to play around with some modifications. But yeah, so this is something we looked at in 2016. Then that actually, when we measure the speed of gravitational waves to correspond to the speed of light, it removes a lot of these very complicated terms. So particularly, we can have this G4 term can no longer have an X dependence, so just having a Brown-Stickett type coupling. And we are left here with a cubic Galilean type term, and the G2 term, which can have a potential and a kinetic term, or even non-canonical kinetic term in this particular case. Now, one thing you can do, however, is that I didn't mention before, is you can move beyond Horndeski theories. The Ostrogatsky theory relies on non-degenerate Lagrangians, and so you can formulate degenerate Lagrangians, which nevertheless still are stable. And people have done that. They've formulated these more general theories, but then they also found here that for those, you would expect gravitational waves to decay in dark energy, into dark energy perturbations, which, of course, since we are observing gravitational waves, doesn't happen. And so you can essentially rule out these additional modifications. And even more, you could actually place some very strong constraints here on this de Lombriser coupling here. So this cubic Galilean type model. And but you can keep on going. And in principle, here with this G2 term, if you had a nonlinear contribution in X, so non-canonical kinetic contribution, you could expect for high energy cosmic rays a Cherenkov radiation into scalar waves, so that you would not be observing these cosmic rays, which can, of course, place constraints on this G2. So in that sense, that we would end up with a very simple Brown-Stickett type theory with potential. But these constraints, they all come with caveats, particularly even the measurement of the speed of gravitational waves, which is that we are dealing here with effective theories, which have they come with a cutoff where the theory just breaks down. And especially if you're interested in dark energy theories, then of course this cutoff could be lower. So that actually, there's a paper a few years ago pointing out that for these type of models, you would expect this cutoff to the theory to break down at energy scales below LIGO, what's been tested with LIGO. And more so, actually, these UV completion terms that we would have to add to the Hordesky action, they reproduce the speed of gravitational waves to correspond to the speed of light. So that LIGO in principle should not have seen any deviation from the speed of gravity, but LISA would be low enough in energy scales it's testing that it should be sensitive to these types of modifications. And the same caveat that I mentioned here is actually applying as well, of course, to this gravitational wave decay, the dark energy perturbations, as well as clearly the Cherenkov radiation. Now, yeah, so that means still interesting work to do in this direction here. But maybe also we should maybe recap the situation that we have on what we know about dark energy. And certainly we already have very good data from cosmological surveys, which tell us that the equation of state is really in very good agreement with cosmological constant. And this is even outdated. I think this by now from the same surveys we have the constraint has improved by maybe a factor of 2, almost a factor of 2. But of course we have this freedom in this action that we can always construct a model that just looks like a cosmological constant, but is not. So something that would be really self-accelerating as a kinetic acceleration without the potential cosmological constant, but would look like it. So, but you have to ask the question, how much engineered is that really? So is this something we should naturally expect? And moreover, in principle, these models could suffer from scale Cherenkov radiation. And certainly, if you want to have a genuine modified gravity self-acceleration, so where the gravity just evolves at late times to produce cosmic acceleration, then this is severely challenged by this gravitational wave speed constraint. And here, of course, there's also again the caveat that perhaps the energy scales that that the theory actually breaks down below the energy that has been tested here. But maybe I should also mention again that, of course, these dark energy models and modified gravity theories that we looking at here, they don't address the old cosmological constant problem of why vacuum energy should not be gravitating. So in a sense, it doesn't really do a very good job at producing a cosmic acceleration that is compatible with data, while also not really addressing the vacuum energy problem. And so what I want to do in the following is look at maybe a simpler approach, just a toy model of how you could go about trying to solve both the old cosmological constant problem and the new problem at once. And so for that, I'm basically returning to the Einstein-Hilbert action and see what we can do about this, and maybe just see if I can do a slight reinterpretation of what we have here. And just for that, I moved the matter sector to the left and the geometric part to the right. And in this case, I just can read it slightly different and say, okay, I see here this matter fields, geodesics is governed by this metric G. And on top of that, I impose the dynamics for G to follow this Einstein-Hilbert action. And in that sense, this becomes a global Lagrange constraint with the Planck mass square being a global Lagrange multiplier. And I should perhaps give a disclaimer here that actually, I'm talking here about a global mechanism, but equally well, you can formulate this as a local theory, which I'm just going to show you a bit later. I think the global version is more instructive to really see what's going on here. And some people may actually recognize some of these things from sequestering mechanism. There's parallels, but there are also important differences, which I can point out when I'm going through the slides. Now, okay, so that means now that we vary this action not just with respect to the metric, which gives us the fields equations, but also with respect to the Planck mass square, which gives this global constraints that relates the cosmological constant to some volume integral over the Ricci scale. And here, importantly, this cosmological constant, that's a total cosmological constant. So I remove here the vacuum terms over here and have a classical free cosmological constant, and the combination of all cosmological constants that just have to equal to this integral, or satisfy this constraint here. So in other words, I can rewrite this using the field equations to find that the total lambda should be equal to 1/2 times the space-time average of T, the trace of the energy momentum tensor, again free of any vacuum contributions, which means that I get these field equations over here, which you can see the cosmological constant is determined by T over here. They don't have any vacuum contributions. In that sense, this field equations, in these field equations, vacuum energy does not gravitate. Now, again, for people familiar with the sequestering, you get here a 1/4 of T, which means that actually vacuum really cancels out in the equation. So you have the same contribution on the left and the right that just cancels. You can recover this in this mechanism as well, as I'll show you later. But for the case I just wrote here down here, you can see that the mechanism works slightly different. It's really a self-tuning that we have, which is that the cosmological classical constant here will just be such that it satisfies its constraints, and so it's self-tuned rather than really cancelled the vacuum dilution. Now, well, yes, as I said, I will just show you then later on how you can realize this in a local scale tensor theory. But yeah, it's just a time model that you can see how, in principle, you can solve the old cosmological constant problem, so that vacuum energy is not gravitating. Now, you could ask the question whether you can also do something about the new problem of the particular value of lambda that we observe. And of course, because we have this relationship that allows you to predict lambda from the space-time average of T, we can try that. So we can, well, assume a spatially perfectly homogeneous matter of the universe. If you plug that in, you see actually lambda would go to 0. So for it to have a finite value for lambda, we would need the universe to collapse at some time, maybe some Higgs instability or something. So we just introduce here an instantaneous collapse for simplicity at some T end. And now we can ask the question, well, when would the universe have to collapse in order to give rise to the observed value of the cosmological constant? And you can compute that, and you find, well, that should have happened 1 billion years in the past. And obviously that didn't happen. You're still here. But you can ask, well, what if the universe would end today or tomorrow? What's the fraction of the observed cosmological constant that we can explain with that? And you find that's roughly 80%, which I think is interesting and close, but not exact. But that's not so much, but the big problem is that we don't have a model that predicts an imminent collapse anytime soon. Or maybe it's not so much a problem than rather fortunate for us. But something that we've really left out in this picture is that, of course, we know that the universe is not perfectly homogeneous. In fact, it's clearly inhomogeneous on small scales. And why does this matter? Now, we integrate here of the future state of the universe, which means that, well, the universe is not going to be just this homogeneous patch or homogeneous density, but then really what happens is that the future observable universe will reduce to the maximum gravitational bound structure around us. So it's essentially the local group, and everything else around it will just be accelerated away and redshifted away in finite time. So that means if you perform now this integral over this observable universe instead, which is a nonlinear calculation, we can do here just spherical collapse equations, assuming some top hat over density, with y being the top hat radius, evolving in terms of the scale factor. Then we can do this computation, and we find that the space-time average of T that we do expect from this picture is consistent with the cosmological constant that would drive cosmic acceleration in the background. And so, yeah, so what we get here is a self-consistent picture with the field equations given here with the free classical radiatively stable cosmological constant. What we have lost, however, with this is that we no longer have a prediction for lambda observed. Although, yeah, vacuum is not gravitating. But we could still ask, well, could we say something about the actual value of lambda? And of course, at least in terms of its energy fraction that we should observe today. And of course, today, the present time, it's inherently something to do with our existence. So we have to really ask the question, well, when would we expect to appear in this cosmic history? And so our variable here is this top hat radius y, dimensional top hat radius, which evolves from 1, close to 1 to 0, or close to 0, depending on whether it's collapsing or not here, multiplied by the scale factor. It's the orange curve, or if it collapses, if it doesn't collapse, it's the green curve below. So it doesn't, for the integral, it doesn't really matter which case you are here in here. But okay, so let's say for a lack of better understanding where, or for better knowledge of where we should appear in this universe, we can do just the simplest thing and just assume a uniform prior on y. And then I should say I will come back to this question a bit later on and try to do a more sophisticated estimate for where you would expect to appear in our universe. But now let's just do this very, very simple thing. We just say, well, uniform prior, so the average expectation for y is that we should be living when y is 1/2. So saying that today should be when y is 1/2. And now, without assuming any cosmological parameters whatsoever, you can make an estimate of what the fraction, the energy density fraction should be in your cosmological constant you would observe at this time t0, by simply saying that the scale factor at that time should be normalized to 1. And you find that that fraction is 70%, which is, as we know, in good agreement with our observations. And in that sense, yeah, it can even, this simple picture, toy model picture, can also provide a solution to the new cosmological constant. And before I go on, I'll also just come back to maybe people that were wondering about this global version of the action, that actually can also recover this phenology here from a local, manifestly local version. And for that, there's different ways you could achieve that. I think the very simple way is just by looking at the scalar tensor theory here with the Jordan-Brown-Stickett type of coupling. You could equally well rephrase this entire thing in Einstein frame if you wanted to. It still works. And so essentially, just let's take this simple action. And what we want to do now is we want to render this scalar field non-dynamical. And in order to do that, again, you could do this in different ways by coupling this with a vector field. But we actually follow here the similar way as is one done in sequestering again, yet again with some differences, that we couple the scalar field here to the field strength of a 3-form gauge field. And now, and again, just for clarity, I'm separating off here the vacuum term from the matter Lagrangian, so that the energy momentum tensor tau is really just referring to matter fields without vacuum. Now, this means now we vary this action with respect to the scalar field, but also with respect, well, the metric, of course, and this 3-form relation with respect to metric gives us this modified field equations, Einstein field equations, and then we get the similar constraint equation we had from before, with the rate in the Ricci scale and the cosmological constant. But importantly, from relation now with respect to the 3-form, we get this constraint here that tells us that, well, that the phi is non-dynamical, or the scale field is non-dynamical on the domain. And now that means that we can combine all of these equations to obtain these Einstein field equations down here. Again, it's a bit more complicated than before. Before we just looked at the case with alpha equals to 0. In principle, we could realize different fractions here, and beta equals to alpha. And then you would have really just the same term as we had before, with delta lambda being some volume weighted field strength of the 3-form here, which we could tend to say, well, maybe this space is much smaller than the volume of our manifold, and this could tend to go to 0. But importantly, all these terms, they're just classical values. So there's no vacuum gravitation in this picture. And as I said, well, we just work with this simple action. I mean, you could work with much more complicated actions. I could return to introducing the entire Hondesky equations or Lagrangians, that it still work, or even go beyond that. It still works. Importantly, it's really due to this x essentially becoming 0 in this case. So far, I've only talked about the matter sector. You could also wonder about graviton loops. This you could also prevent from gravitating, or the contribution of vacuum to prevent from gravitating by introducing a coupling of the scale of maybe another scalar field to a Gauss-Bonnet term. You could then maybe even rephrase that again as a scalar tensor theory. So there's lots of things that, well, you can look this up in the papers if you're interested. Maybe for this talk here, it's more maybe some other questions that one can wonder about is, for instance, if there's any signatures of this that we could see in our universe. And in principle, it's really difficult, of course, if our entire observable spacetime would be in a regime where this scale field is fixed. But in principle, you could think about some coupling that may only operate in certain space-time regions and not in others. So maybe similar like a screening mechanism. And here, just really crudely, we introduced the Heaviside step function, which tells us that in some regions there is a 0 contribution here, in which case the scalar field remains dynamical. And when we have this decoupling, then the scalar field becomes fixed. So in that sense, there could be maybe at early times the gravitational coupling could be evolving, or maybe also maybe in space there are regions where the gravitational coupling can evolve, and others where it's fixed. And of course, it also means the value it's fixed to between these different space-time regions doesn't necessarily have to be the same. And you can generalize this picture as well by just saying, okay, we can generalize this to other couplings. For instance, let's say we take the electromagnetic action here, Lagrangian here, and then this would introduce an evolution of the fine structure constant of the masses of particles, like the electron mass, and you could even change the speed at which these interactions propagate. And then again, they could be fixed in some parts and evolve in other parts, and arise and assume different values in different places. In that sense, of course, what this sort of motivates is a multiverse picture of interactions that we can get. And one thing, of course, we could go is to look and see if there is, if some of these regions where these couplings are evolving overlap with our observable universe. And then we would expect, of course, some signatures of new physics here. But of course, you know, this is by far not the only model which would suggest that this is a good idea to go and look in the cosmological data for any signatures of new physics. We're actually going to get really good data soon with surveys like Euclid analysis T from galaxies, and particularly, however, in the nonlinear regime, I should say. So that means if you really want to make use of this data, we ought to be able to predict the matter power spectrum for a start down to rather nonlinear scales of 10 megaparsec inverse. And this is already difficult enough with lambda CDM, because of course it's very nonlinear, but also means that these scales you have baryonic feedback effects entering that you need to model. And now you would want to do that even with any type of new physics model that you could think of. And in order to make that feasible, to make these predictions, we worked out a formalism which we call the reaction formalism, and even also developed the code here, the REACT code, which uses perturbation theory. We started with linear theory, but also higher orders to get the loop corrections. But that doesn't go nonlinear enough, so we add on a halo model prescription that really allows us to reach these scales, which means where we implement modifications in the way the halo forms through the modifications on the spherical collapse, as well as the virial density that enters here. And I should say this is really just theoretical computations. There's no fitting involved to do, for these models at least. So what we can do or want to do here is model the reaction of a lambda CDM matter power spectrum with the introduction or to the introduction of new physics. And this is done here, for instance, for DGP gravity. So it's a high dimensional brain world model which allows gravity to leak into higher dimensions and can so that essentially is modified at large scales. But this also introduces a skinning mechanism which makes things more complicated on nonlinear scales. And again, so this is any DGP particular fitting involved here, because you can just use a lambda CDM emulator or simulation or so, and then you model theoretically this reaction on top of it. And you can see that this works rather well here. We can get, depending on redshift, get the 2% agreement with simulations down to K of roughly 5 megaparsec inverse. And of course, we also went and looked at other models, and it still works very well. As again, there's no particular reason it should work for this model better than for others. So people can use this code to produce nonlinear power spectra for their favorite models. But of course, I mean, reproducing simulations is one thing. If you want to reproduce, well, use this to compare against observations, we ought to include here massive neutrinos and baryonic effects, which we have done so very recently, and it still works very well. You can do this in a modular way. Also, we don't just have weak lensing data, we also have the galaxy power spectrum, and in redshift space that we need to include the modeling of velocities, and there's also work in this direction. And since we want to make this very user-friendly, we're also working on a module that essentially allows you, so it's actor-reactor, allows you to take your favorite model and start with the Hodesky theory, and you can implement that. It's basically like a plug-and-play module that produces you then the required inputs for the REACT code that will then provide you the nonlinear power spectrum. However, even if you have now a code like this, which is actually also pretty fast in producing these nonlinear power spectra, it's a good accuracy already. But even if you have this, you have to ask the question of how do we go about testing for new physics in our cosmological data? And typically, the way this is done is essentially on a model-by-model basis. We just take one model, do an MCMC analysis, see whether it fits or not, or whether we need to dismiss the model, or we want to investigate it further. And so we said, well, maybe a more efficient way we could do is by actually developing a neural network to train these different nonlinear matter power spectra that lots of different models produce, of course, also with a lot of different cosmological configurations. And we've done here some prototype of that. Yeah, so you train that, and what it can do now is when it receives a observation of the matter power spectrum, it can quickly tell you whether there's a signature, if anything that doesn't look like standard cosmology in there. But not only that, it can also say, well, which type of models would actually be interested in these models to explain a signature like that. So rather that you don't need to just go model by model and just at some point be lucky that you have something that matches the signature, but it can much more focused find the models that are interesting and perform your MCU's analysis on those. But yeah, I also promised earlier on that I would talk a bit better about this, the why now problem, and the question of where we would really expect ourselves to be in cosmic history, and so why we should expect the energy density or in the cosmological constant to compare to that of matter today. And of course, again, this requires a notion of what today is, where our presence in cosmic history should be, and well, at least for the type of life we are or we know of, we would expect to be living somewhere around the star that would host us. So certainly one thing that we need is a star, so we can look at star formation history throughout the cosmic history. And you find that peaks roughly 4 billion years after the Big Bang. And we are here rather at the tail end of this. So maybe not the most typical place. But then, of course, also we tend to prefer some cooler places than the stars, so maybe, and rocky surfaces, so we can look at terrestrial planets that form around these stars. And of course, the first stars will not be suitable because we also need the metallicity to build up throughout cosmic history so that we can actually build terrestrial planets. And here's a bit more rough calculation, but yeah, you can do this computation and you get the formation distribution through cosmic time that tells us that it should have, terrestrial planet formation should have peaked roughly 5 billion years in the past. But of course, once we have a planet, we also need life to allow some time to form on these planets. And for lack of better knowledge, let's just take the prior from our experience on Earth and say, well, this takes roughly 4.5 billion years. And so then we find that the emergence of observers should really peak very closely to today. And in that sense, you could say, well, it doesn't seem that there's really a why now problem in our universe. We just really happen exactly to appear where we're very likely to. But now you could say, this is for our universe. Perhaps you would want to study where life appears in other universes, where you change cosmological parameters or even fundamental parameters. And when you do that, maybe you want to have another notion of cosmic evolution of time. And there's many ways you could do this. Here, just as an example, what you could do is you say, well, I compare the orders of magnitude between the horizon size of the universe to the proton size, just taking this as an dimensionless value. Variable, and you just say, well, proton size because it's the fundamental building block of molecules or atoms, molecules, and eventually life. And so you can look at how in our universe, the cosmic evolution here, you can find recombination here when these different sizes were separated by roughly 40 and 41 orders of magnitude. And then you find that we appeared here when they are separated by 42 orders of magnitude. And in that sense, maybe 42 indeed has something to say about life, the universe, and everything. And you can now wonder, well, what happens here when you change, and this is just for our universe, what happens if you move to other universes that have different cosmological parameters and fundamental laws and parameters? And in order to compute that, we've started developing here what we sort of call fittingly the alpha version of deep thought. And that's computing the the relative likelihood of formation of observers given as a function of cosmological and fundamental parameters. And with that, of course, you would like to produce a likelihood that can tell you, whether you're more likely to, where we would be more likely to appear in one universe or another. And in that way, you could ask, of course, maybe whether we are in the best of all possible worlds or not. And if we are not, then the question is why this is not. Maybe perhaps there's more fundamental theory that connects the parameters or doesn't allow you to to realize certain configurations of parameter space which would be very habitable, but they're just not possible. And so you actually can go about and do Bayesian evidence between different fundamental theories. And perhaps, of course, if we find that we're not very likely, it could of course also mean that there is no multiverse. But it's certainly a calculation very worthwhile doing, also because it allows us to really understand all the physical process to go into the emergence of life, or at least, let's say, from astrophysical point of view, from the emergence of terrestrial planets. But of course, there are some priors you can place on when life certainly would not be possible. Right, and just to give you some examples of what we can do here, we can go and look at cosmic coincidences across the multiverse. Here, just varying cosmological parameters for a start. Because cosmic coincidences, often people look at this and wonder whether there is any particular physical reasons why we have this coincidence that could maybe point to some fundamental connection or physical law that could be extracted. And so here we see just this. Well, of course, very well known is the coincidence that we have at the epoch of recombination with the equality in matter and radiation, or here more specifically with the equality of baryonic energy density of photons. And here on the other end, we have the equality between the cosmological constant and baryons, which happens at the star formation peak. Now, this is just a reformulation of the why now problem, because of course, stars formation has something to do with our appearance in the universe. And there's another coincidence intertwined here that the baryonic energy density and that of the cold dark matter or total matter is also quite similar. I mean, it could be separated by many more orders of magnitude than we have. So yeah, this is another known coincidence. Certainly less well known is that we also get a coincidence here at the ionization epoch between the cosmological constant energy density and that of photons. And of course, you could wonder whether there's some physical reasons for all of that. I mean, it's interesting, for instance, to think that all of these epochs they revolve around hydrogen physics. Now, there's just another way of rephrasing these coincidences. They give just the relative contributions of cosmological constant and matter and the inflection points that we look here. And you can see, well, if you look at the inflection point here from the matter and cosmological constant dominance, then this is very close to, it's basically, very close to today. For matter, notice the cosmological constant and baryons, we get this here at the star formation peak, and then the ionization time, or instantaneous ionization time over here for photons compared to cosmological constant. And this is, of course, the coincidence from before, the why now problem, the appearance of observers in our universe. And now we can vary our parameters. So here we vary the cosmological parameters. Alpha just means that's just the relative change, or just the weighting of the energy density of the respective parameter. For omega for rho matter, which we can change here, for instance, by 2. Well, actually, total 4 over 4 orders magnitude. And there's a number of things you can take from these plots. Perhaps we can look at this here, for instance. This is here in the rows, we're comparing recombination redshift, ionization, star formation, and our estimate for when life should appear. I should also say that time today is fixed to when the temperature, the CMB temperature reaches 2.7 Kelvin. So just as in our universe. And so for instance here, you can see that when we cruise the baryonic density, we get this. It's not very well visible here. It's just, you can better see it in a correlation plot. It's when the recombination redshift goes slightly up, and so does the equality between the photon energy density that of baryons. And the reason, of course, that they are related is, of course, the psi because they enter the psi equation. So that's not very surprising. Maybe more surprising is this plot here, that you can see that when we change when we increase the energy density of the cosmological constant, that the ionization redshift really scales the same way as the redshift of photon and cosmological constant equality. And down here we can see the why now problem, that for universes with our matter density and larger, the ionization, the redshift of equality in the matter and cosmological constant scales the same way as the redshift that we estimate life to appear. So yeah, certainly some universes will run into the same why now problem. But we can also ask the question, well, how many of these universes would have all the three coincidences that we've seen before? And you can do these calculations here, just our samples of these different universes that we sampled. And here, of course, because we fixed the temperature today to be 2.7 Kelvin, of course, omega r h squared will be a constant. But you can see, so this is just the blue, all samples, but the red ones are the ones where all three coincidences would appear. We can see there's actually a restricted range between the Hubble parameter between 0.5 and 1. We also here, omega bh squared should be constant. And the reason for that is, of course, because we want our recombination, our coincidence at the recombination epoch. But maybe more surprising is this parameter relation here, or combination here with sigma 8 times omega lambda h squared, which is constant, or rough, this was well constrained, which really comes from the star formation rate and that we impose a coincidence at the reionization epoch. Yeah, so I mean, this is just some examples, but really what we want to do now is use this code to produce these likelihoods in formation of life as a dependence of cosmological and fundamental parameters. But yeah, I already used enough time here, so I want to conclude here and just leave the conclusions here for you to read, and I thank you for your attention.